Hello, welcome back to SCI Teach. So this is a continuation of the chemistry revisions, and we are still on SS1. We've done the first part and the second part, and this part is one which will round up SS1. So we're going to be concluding with SS1 topics, and we're starting from where we stopped, and we're starting from acid, bases, and salts. So acid. Remember to subscribe to this channel so that you get enriching resources for your academic excellence, and also share these videos, share this content to your friends that are students, science students, so that they can prepare for exams and pass them with good grades. All right. Thank you. So acids. An acid is a substance which produces hydrogen ions, and we call it protons, and that as the only positive ion when you dissolve that substance in water. That's to say, an acid is a substance which, when you dissolve such a substance in water, will yield hydrogen ion. There will be other ions, but hydrogen ion will be the only ion with a positive charge. Then when that happens, that substance you dissolved in water is an acid. And remember from the previous videos, when you dissolve something in water, then that thing is an aqueous solution. Aqueous solutions are solutions in which water is the solvent. Solvent is what dissolves a solute, like what should be dissolved. Okay, so if that's the case, then we can also say that an acid is a substance which yields hydrogen ions as the only positive ions in aqueous solutions. All right. Now we know that all acids contain hydrogen, because we say all hydrogens or all substances that will yield hydrogen ions as a positive ion, only positive ion, is an acid. That means all acids contain hydrogen ions. But although all acids contain hydrogen ion, not all the hydrogen atoms in a substance can be ionized, can dissociate into hydrogen ions. Okay? Hydrogen in atom form needs to be dissociated. You put a substance in water, if that substance is acid, the hydrogen atoms in that substance has to dissolve in that water. That's to say, the ions in that atom has to dissociate into the water and form ions. But not all acids dissociate their ions the same way. So there are some that will dissolve those ions in water faster or more than others. So those hydrogen that dissociate can, do so in different degrees. The ones that dissociate completely in water to give hydrogen ions are called strong acids. The one that will dissociate all. Let me give you an instance that you can picture. Let's say you buy lollipop, lollipop, and then you also buy chocolate candy. Chocolate. I'm using now physical means, but I'm trying to make you picture something. You have a chocolate bar, which is a candy, but which is not hard. Chocolate bars will be semi-solid. It'll be soft. You can even chew it. It's chewy candy. But lollipop is hard. Let's say you take two of them and put them in water and leave them for a while. After 2 hours, maybe you come back and all the chocolate is dissolved, but the candy or the lollipop is not. Now let's use that picture. That's not a perfect picture, but let's use that picture in understanding what I want to say now. I said not all acids, or all acids will dissociate or will dissolve their hydrogen atoms into water, and when it dissolves in water, an ion, hydrogen ion. Not all acids do that the same way. Just like the candy, the lollipop and the chocolate, some acids will dissolve all their atoms of hydrogen into the water and it becomes ion, some will not dissolve all. Others will take a long time to do that and will still not dissociate all. The case may be. Others take very fast to dissociate all of them. That is the different degree of ionization I'm talking about right now. The ones like the chocolate bar that could dissociate all its ions into water is a strong acid, because the water is going to have a lot of hydrogen ions, and remember, hydrogen ions are what make acids. If the hydrogen is still in atomic form, it's not dissolved into the water, then the acid is weak. So the substances which dissociate all the acids which dissociate all its atoms into the water to form ions are strong acids, while the opposite are weak acids. So we have strong acids like hydrochloric acid, triazonitrate 5 acid, and in fact, just know that all natural acids are weak acids. Well, in addition to hydrogen fluoride. But how do you know natural acids? You see the names are sweet names, or maybe not sweet, but peculiar names, not like the other names, like acetic acid, formic acid, okay, citric acid. Those are natural acids. See, they are found in living things. They're found in plants. If they were to be strong acids, you won't eat those plants and survive it. But because they are weak acids, especially when the fruits are ripe, and then it's a sign to tell you that all natural acids are weak acids. There is lactic acid in milk, but if you don't take milk in too large quantity, you see, you don't purge. It's just normal. But you don't even take the amount of hydrochloric acid as you would even take 1 teaspoon of something, milk, and not face consequences. So that's what I'm trying to say. I'm just giving you a hint on how to know strong acids or weak acids. Strong acids, hydrochloric acid, H2SO4, all that, H2SO3. And then weak acids, formic acid, nitric acid. No, nitric acid is triazonitrate. It's not. Acetic acid, ethanoic acid, all those are derived from plants, and they are weak acids. Alright? Now, acids can also be concentrated or dilute. This is what I mean. If you bring a bottle of Coke and then you turn that bottle, the Coke into 2 cups equally, and then in 1 cup you put in maybe about 50 drops of water, just drops, 50. Then on the other cup you put in 1 liter of water. From your own analysis, which cup will taste better? Of course, the one that has just drops of water, because the amount of water, amount of solvent you added to that Coke is less than the amount of Coke in there. So when the amount of Coke is more than the amount of water added, then it's concentrated. But on the other cup, the amount of water added to that Coke is more than the amount of Coke in that cup. When the amount of water is more than the amount of the Coke, then that is a dilute Coke solution. The same goes to concentrated and dilute acids. When you have more solvent, like water, in an acid, the volume of water is more than that of the acid, then that's a dilute acid. But if the volume of acid in that solution is more than the solvent, like the water, then that's a concentrated acid. Okay? Now, basicity of an acid. You know, all acids in aqueous solution yield hydrogen ions. We've said that already. But these hydrogen ions can be replaced by metallic ions. I'm sure you've been taught that. That's to say, if I have hydrochloric acid, HCl, and then in a solution, and then I bring in zinc metal or aluminum foil, cut them into pieces and drop it into that solution, you'll see some fizzy, some bubbles start to come out. That's a reaction showing that the aluminum metal or any metal is replacing hydrogen. That is, hydrogen was hydrochloric acid was HCl. This zinc or the aluminum goes in, removes hydrogen and takes its place, and it now becomes aluminum chloride or zinc chloride, ZnCl2. Now you see the hydrogen, since it's a gas, tries to come out, and then you see those small bubbles since it's a gas. Now that means that all the hydrogen ions in acids can be replaced, maybe not all, can be replaced by metallic ions. So the number of such hydrogen ions, the replaceable hydrogen ions that are present in 1 mole of an acid, is what we call the basicity of that acid. In other words, the number of hydrogen atoms present in a formula, let's just use that formula of the acid, is the basicity of that acid. Like hydrochloric acid, you see one H plus ion and one Cl minus ion. So H, one of them, and one Cl came in to make HCl. It has only one hydrogen atom. That's the only hydrogen atom that can be replaced by metallic ions. So that means the basicity of HCl is 1, or you call it monobasic. H2SO4, sulfuric acid, has 2 hydrogen atoms, and it's only those 2 that can be replaced. So the basicity of H2SO4 is 2 because it has 2 hydrogen atoms. Same way, H3PO4 basicity will be 3 because there is only 3 hydrogen atoms. Now let's look at the physical properties of acids. Dilute acids have a sour taste. Of course, if you taste lime, it slaps. That's the sour taste to show you that lime contains dilute acids. So everything that slaps you gives you a sign that it contains acids. It's acidic. Not all. Then acids turn blue litmus to red. If you take a blue litmus paper and put it into a substance which is acidic, that litmus paper will turn to red color. So the degree of how dark the red is shows you how concentrated the acid is. Not in all cases. A very dilute acid will usually show turn blue litmus paper to red. Depends on the pH of the medium. Then the concentrated forms of strong acids like HCl and H2SO4 are corrosive. Of course, from the word corrosive, you can sense corrosion and cause a metal to rust. Okay. Now the chemical properties of acids. Number 1, acids react with some metals, like we've already explained, to liberate hydrogen gas. So when a metal goes into a solution of an acid, it displaces hydrogen. That's one chemical property of acid. Then that can also be a preparation for hydrogen. How to prepare hydrogen? Put a metal into an acid, hydrogen comes out, and you trap it and get it. Acids react with insoluble bases. Insoluble does not dissolve in water. Remember, when we get to base, we discuss that insoluble and soluble ones. So acids react with insoluble bases to form salts and water as the only product. So that's what you do in your laboratory. First practical, you do titration, neutralization reaction, where you titrate an acid with a base, and when you form a neutral substance, that is a solution that contains acid and water. Okay. Then acids react with trioxocarbonate 4 to liberate carbon 4 oxide. Take note of all this. Acid reacts with metals to liberate hydrogen gas. Acid reacts with trioxocarbonate 4 to liberate carbon dioxide. How do you prepare acids? By the reaction between an acid oxide of a metal, that's an acidic anhydride, and water. So if you react an acidic oxide of a non-metal with water, then you form an acid, and that is the general method. WAEC may ask, JAM may ask, NECO may ask, objective, which of the following is the general method of preparing acids? The answer is the reaction between an acidic oxide of non-metal, or we simply say reaction between an acidic anhydride with water. That's the general method. Also, you can prepare acids by the displacement of a weaker or more volatile acid from its salt by a stronger or less volatile acid. Or another one, the direct combination of constituent elements. That's a synthetic method. This one is a simple thing. You want to cook something with rice. Maybe you start with boiling, but whatever it is, you keep adding the ingredients. So I could say to prepare rice, you directly add the constituent elements, add all the ingredients, and then it makes up rice or soup or whatever you're making. That's how direct combination of constituent elements is. You want to make H2SO4, okay, fine. Add S, sulfur and oxygen, combine them the right proportion with hydrogen, and you form H2SO4. Alright, so now what are the uses of acids? Acids are used in chemical industries to make fertilizers, detergents, and drugs. So I have a feeling that students always feel acid is the enemy and base is the friend. No, acids are the reasons why you cure some of your illnesses. Your drugs are made from acids, made of acids. Since the illness is harsh, it needs harsh stuff to fight it. So acids are not the enemy. Acids can be useful. And one of the ways is that acids are used in the chemical industries to make fertilizers, to make detergents, to make drugs. They are used in industrial processes as drying agents. Okay, H2SO4 is a drying agent. They are also oxidizing agents, and they are also catalysts. Also, hydrochloric acid, one type of acid, can be used to remove rust. Okay, so remember that the concentrated forms of these strong acids can be corrosive, so you wear a glove in the lab before you touch even the bottles containing them. Alright, it's important to note that if you are handling acids and it's accidentally spills into your mouth or eye, it may cause serious irritations, even if it's on your skin, and may even blind your eye if you're not careful. So you, as a solution, if it spills on your body, you go to a running tap. Of course, a tap is in your lab, and then you wash it away. Don't scrub it, just allow the water to be rolling on it and going. Don't use a stagnant water. So don't wash it inside a basin. Use a running water. It keeps washing away the acid. Don't rub it. Allow it to wash down. Same thing if it was in your eye. Put your eye under the tap, and then the water keep running, and it's reducing the concentration of the acid on your eye slowly till it is dilute and then not there anymore. Same thing with your mouth. Just put water in your mouth. Don't swallow. Pour it out. Put another one. Rinse. Pour it out. Put another one. Rinse. Pour it out. Just keep doing that till everything is out, to avoid taking in too harsh or concentrated acids that can damage skin, eye, irritates different parts of your body. Then if you are mixing acids, if you are diluting acids, be careful not to add water to the acid. Please add acid to water. Use this as a point of reference. You don't add water to hot oil. Do you do that? No. But you can add hot oil, water. You can add oil to water, whether hot or cold. It's safer. So add acid to water. Don't add water to acid. It may spill vigorously, because just like your water in hot oil will spill vigorously, it may spill and you won't know where to touch on, because irritations. All right, let's go ahead. Chemical industry. The chemical industry is defined as one, that's an industry that uses chemistry to make chemicals from other chemical substances. So we have examples like the brewery, make drinks, they brew drinks, textile industry, plastic industry, refining industry, cement industry, food industry, pharmaceutical, fertilizer industry, metallurgical industry, paint industries, soap and detergent industries, ceramic industries, rubber and glass industries. Those are chemical industries because they're going to use chemicals to make whatever they're making. Right? Now, so how do we divide the chemical industries? Okay, we have the basic chemicals like the acids, the bases, the alkalis, the salts, and the organic chemicals. Chemical products used as starting materials in other industries that manufacture substances such as paints, fertilizers, and explosives. We have all that chemical industries can produce. They can also produce chemical products that are used in the manufacture of artificial fibers and plastics. Then we have another set chemical products such as cosmetics, drugs, and soap can also be produced in the chemical industry for your personal use. So now, but how do we divide them? How do we group them? We divide them into two: heavy chemicals and fine chemicals. Heavy chemicals are chemicals that are manufactured in large quantities. Okay, the most useful basic chemicals that the chemical industry make is hydrogen tetraoxosulfate 6 acid. Okay, it's used in many chemical processes. That's from making fertilizers, cleaning, steel. Sodium hydroxide also for making soap and other things is produced in large quantities, so it's a heavy chemical. Ammonia is another one. It's manufactured in large quantities and is used to make fertilizers as well as explosives. So I've given you what a heavy chemical is. I can easily say heavy chemicals are chemicals that are manufactured in large quantities, maybe not to a high degree of purity, if you want to add that. And I've given you 3 examples. I said the one that is most useful example is hydrogen tetraoxosulfate 6, which is used in making fertilizers or cleaning steel. And I've given you another one, sodium hydroxide, which is used in making soaps and other stuff. And then last one, ammonia, which is used in making fertilizer and even explosives. Those are heavy chemicals. Now, fine chemicals are chemicals that are produced in small quantities and produced to a high degree of purity. Like drugs. Drugs are not produced in large quantities in such. You see, it finishes. Some people may not have another cell because it has to be produced to a high degree of purity. Okay, think of it like this. Super glue. If I give you 1 liter of super glue, you see it's very expensive compared to 1 liter of water, because that liquid, the super glue liquid, is a fine chemical. It's produced in small quantities. You see, when they sell it, it's just a little quantity and it's costlier than 20 liters of water. So what I'm saying is fine chemicals are produced in small quantities, like drugs, fragrances, perfumes. You see, they don't produce perfume in large quantities. Pigments, all those. Okay, they are much more expensive than the heavy chemicals. All right, so factors to consider when siting a chemical industry: that industry should be near to raw materials, where you buy your feedstock, where you get your stock. Also, labor supply. Are there workers that will work? The people that will work, are there laborers that will work? Consider that also. Transportation. Is it easy to transport the goods from the company or from the industry to the market? or from the raw material market to the industry, transportation. Is there an accessible road? You know that. Then nearness to power supply. Is there power? If there is power, am I close to where power is supplied? If not, it can hamper or can make industry running very expensive. Then government policy. The government of that country or the place I'm citing my industry, what is their policy about this type of industries? Consider that also, because you can finish building and not use it. Then, is it away from residential area? Very important, because it could have dangerous chemicals, could have noise pollution, so it has to be away from the residential areas. Also, is there availability of water? So I see most industries are sited close to a river, close to rivers, streams, stuff like that, because you need water every single day in running the industry or the systems or the machines. Now, what are the effects of chemical industry in a community in which it is sited? You see, there is improvement in the standard of living, there is empowerment or employment opportunities, there is development in the community, there is pollution. So economic importance then. Pollution, air, water, noise, thermal pollution, and then has social effects also. So I said we'll not be dwelling on areas we won't really see in oil. We'll go straight to the point. So we've done acids now, that's all. We'll do base or an alkali. So a base is a substance that produces hydroxide ions when dissolved in water. Remember, acids produced hydrogen ions as the only positive ions. But a base will produce hydroxide ions. Once it produces hydroxide ions, then that is a base. So now, some bases can dissolve in water, just like we discussed concentrated weak and strong acids. Some bases can dissolve in water, others cannot dissolve in water. Maybe very little amounts dissolve in water, but you still see the solids. Even when you keep stirring, it doesn't dissolve. Some are like that. The ones that dissolve, as the soluble hydroxide, we call it alkali. So that's why we say base or alkali. Bases and alkalis. So it's generally a base once it produces hydroxide ions. Now, this base we're talking about, can it dissolve in water? If yes, then you call it alkali. If it can't dissolve in water, then it's just base like normal. That's why we have to say bases and alkalis, right? So we can therefore define alkali as a basic hydroxide, okay, which is soluble in water. Now, neutralization, an acid turns blue litmus red, and then an alkali turns red litmus blue. If an acid is gradually added to an alkali, there will be a stage where the solution becomes neutral to litmus. That litmus color becomes unchanged, or just that purple color it had. That will indicate that the solution is neither acidic nor basic. That's not acidic, not alkaline. Okay? The ones you're going to use in titration is alkali, because if it doesn't dissolve in water, you can't use the solution. So all the ones you use in your titration are alkalis, because they are soluble in water. Acids and bases react with one another to yield two products, salt and water. We know that. So if acid like HCl reacts with base like or alkali like sodium hydroxide, the salt that will form with sodium chloride, a common salt, a table salt, and water. Okay? So neutralization is a process in which an acid reacts completely with an appropriate amount of a base or alkali to produce a salt and water only. Okay? So since a base neutralizes an acid, bases can also be defined as substances which will neutralize an acid to yield a salt and water only. What are the physical properties of alkalis as bases? Alkalis have a bitter taste. The taste is bitter. We said acids have sour taste, and we can see that in fruits. So nobody went to taste hydrochloric acid to say, oh, it's sour. You see that in fruits. It's dilute acids. Alkalis have bitter taste. If you taste your soap, you will see it's bitter, because sodium hydroxide, potassium hydroxide, alkalis are used to make soap. Alkalis are soapy to the touch. They feel slippery. If you touch it, It's like you touched a soap, slippery. Okay, but don't touch it. Don't touch it. You do not know how concentrated it is. Okay, alkalis turn red litmus to blue. Okay, acids turn blue litmus to red, but bases, alkalis turn red litmus back to blue. Not back to blue, but to blue. Concentrated forms of the two caustic alkalis, sodium hydroxide and potassium hydroxide, are corrosive. So if sodium hydroxide, even though it's a base, can still injure your skin, can still irritate your skin if they are in concentrated forms, sodium hydroxide and potassium hydroxide. What are the chemical properties? All bases react with acids to form salt and water. We've said that under neutralization reactions. Then alkalis react with ammonium salts in the presence of heat to generate ammonia gas. So ammonia gas can be prepared by reacting an alkali with ammonium salts. So the reaction can be used to test for alkali, right? What are the uses of bases, alkalis? Sodium hydroxide is used in the manufacture of soap, sodium salts, and plastics. It is also used to refine petrol. Okay? Also, potassium hydroxide, KOH, is used in the manufacture of liquid soap, but it can also be used in dyeing and electroplating. Also, calcium hydroxide is used in the manufacture of mortar, cement, and plaster, but you can also use it to neutralize acidic soils. Then magnesium hydroxide, these similar things I've said here is hydroxide because bases contain hydroxide ions. So magnesium hydroxide, MgOH, can be used in the manufacture of toothpaste, magnesium of course, but it can also be used as a laxative. And lastly, aqueous ammonia is used for bleaching clothes and as a detergent. So that's to say bleaches are alkaline, not acidic. Right, pH. pH means potential of hydrogen. So pH scale is defined as the measure of the acidity or alkalinity of a solution. How acidic is a solution, or how basic, how alkaline is it? The pH scale measures that. And pH formula is pH equal to minus log to base 10 of the hydrogen ions concentration. Okay? So if you are given an equation, you write the formula and input your values, solve it appropriately, and you have your answer. Then when you have your answer, you check the scale, the pH scale. The answer shows you if that substance is acidic or alkaline. pH scale can be in your head, okay, because you know that pH scale has values of ranging from 0 to 14. 0 means from 0 to 6.9. 6 is acidic. So the far left, 0 is strongly acidic, 1 is strongly acidic, 2 is strongly acidic, but the acidity reduces as the number increases. 3 is not as acidic as 2, 4 is not as acidic as 3, 5 is not as acidic as 4, and 6 is not as acidic as 5. 6 is weak acid, and then 7 is neutral. That's where you have water. Then you go to 8, they are going alkaline now. 8 is a weak alkali, keep going in, increasing in alkalinity till reach 14, which is a very strong alkali. So 0 to 6 and 6.9 is acidic, 7 is neutral, and from 7.1 to 14 is alkaline. Alright? Now there are different concepts of acids and base. So many scientists defined acids and base in different ways. Let's consider them. Like Arrhenius, the Arrhenius concept of acids and base. Arrhenius said that, number 1, acids are substances which, on dissolving in water, would dissociate to produce hydrogen ions as the only positive ions. Of course. But that a base is a substance which combines with H plus ions to form water. Okay? Like if you say copper oxide, CuO plus 2H ions will form Cu2 plus water. So water is formed. So according to Arrhenius, that's the definition of acid and base. Then we have another one, Bronsted, Lowry, concept of acid and base. The two names, Bronsted and Lowry, combined to form it. So you could say Bronsted and Lowry concept, or we just simply call it Bronsted-Lowry concept of acid and base. Said that acid is a substance which will donate protons to a base. So according to Bronsted-Lowry, acids are proton donors. So but a base is a substance which will accept protons from an acid. So according to Bronsted and Lowry, a base is a proton acceptor. Right? Note this, that Bronsted and Lowry concept is where you have conjugate base, or maybe conjugate acids also. That's what I'm saying is, if you have an acid HCl, and then that HCl loses one hydrogen atom, HCl uses one hydrogen atom, what is left behind is Cl minus. That what is left behind is now a conjugate base. Okay, so that's is found in Bronsted and Lowry concept. Alright, so a conjugate base is formed when an acid loses one proton. If it was H2SO4, that one has two hydrogen atoms. If it loses one, that becomes HSO4 minus. Then that HSO4 minus is a conjugate base of the acid H2SO4 because it has lost one hydrogen atoms. That's the idea of conjugate base or acid. Conjugate acid can then be an acid, a former conjugate base, that HSO4 minus, that gains another hydrogen atoms and becomes back H2SO4. Okay. Now Lewis' theory of acids is another theory. Lewis acid is a substance which can accept a pair of electrons to form a coordinate linkage. That's electron acceptor. Okay. So like we say Cu2 plus, H plus, Fe2 plus are all Lewis acids because they are able to accept electrons. Also, atoms, ions or molecules with an incomplete octet of electrons are Lewis acids. Okay, so take note that Lewis acids are electrophilic, and then Lewis base is a substance which can donate a pair of electrons to form a coordinate covalent bond. Okay, that's electron donor now. So anions like hydrogen ion, Cl minus, etc., they are compounds with lone pair electrons. All these are Lewis bases. And also remember that Lewis base is nucleophilic. Alright? Now let's move to the next subtopic, indicators. Of course, you know that indicators are weak organic acids or bases which will produce different colors in solution according to the hydrogen ion concentration. In other words, according to the pH of that solution. Okay, so you have different types of acid-base indicators. You have methyl orange, which is red in acid but yellow in base and changes according to the range, maybe 3.2 to 4.4 pH. Methyl red, yellow in acid, red in base, phenol red, you have phenolphthalein, you have litmus, you have all those indicators. Okay, all right. And in acid-base titration, remember that acid-base titration is an experimental procedure, first of all, that is used to determine the unknown concentration of an acid or a base by precisely neutralizing it with an acid or a base of known concentration. So you know the concentration of one, maybe the acid, or you don't know that of the base. That means the base is what you're trying to find its concentration. Or you know the concentration of the base, 1 mole or 2 moles or 0.1 molar base. That means you won't know the concentration of the acid and you want to find that. That's how titration is done. There's something we call buffer solutions. Okay, so buffer solutions are solutions which does not change its pH due to slight addition of acids or base. Okay, so if it was let me give you a perfect example. Our blood have buffers. That's why you can take injections and not be destabilized. If our body has buffers. That's what I wanted to say. Our body has buffers that You can eat something that is harsh, and instead of dying, you purge and remove it. Not that really that's buffer, but you can eat something that normally should. You kill worms, kill some things, and then you see you are alive because you have buffers in you that can, as long as the addition of those acids or harsh stuff in your body, is acid for buffers, bases. They are just little additions, then it can stabilize itself back. That's why buffers must be added to injections, drugs, so that it won't go into the system and change the pH of the blood, because a slight change in pH of the blood can cause death. It's fatal. Okay, so buffer solutions are widely used in processed foods and drinks to prevent excess acidity. Okay, so take note of this. A buffer solution contains a weak acid and a weak base. A weak acid and a weak base. You will see so that if a base comes in, the acid neutralizes just a little. If the acid comes in, the base neutralizes. So that helps the system stay without changing pH. Example is ethanoic acid plus sodium ethanoate. That's an example of the weak acid and the weak base that can be found in buffers. Now we go to salts. We don't acid bases. Now we are in salt. A salt is a compound that is formed when all or part of the ionizable hydrogen ions of an acid is replaced by metallic or ammonium ions. So we said metals can replace the hydrogen ions. When they replace them, then you form a salt. Alright, there are different types of salt. We have normal salts, like these salts that have neither hydrogen nor hydroxide in its formula. NaCl, see, no hydrogen, no hydroxide, then that's a normal salt. Okay, then we have acidic salts. They are formed as a result of the reaction between a strong acid and a weak base. So because the acid was stronger than the base, the hydrogen ions of the acid will still be present in the formula. So in other words, acidic salts still have hydrogen ions in their formula for you to know, like NaHSO4, NaHCO3, NH4, okay, NaH2PO2. All those are acidic salts. Then basic salts, unlike the acidic salts, is formed as a result of the reaction between a weak acid now, but then a strong base. So because the base is stronger than the acid, there will still be the presence of the hydroxide ions that are found in bases. So that means, in other words, basic salts will have OH in their formula, like MgOHCl, CaOH2, calcium hydroxide, CaOHCl, MgOH, NO3 are basic salts. Then we have double salts. This one are salts which ionize to produce three different types of ions in solution. Usually the two of these ions will be positively charged, while the other will be negatively charged, like KAlSO4. K is positive, aluminium also is positive, but SO4 is negative. So it has three types of ions, two are positive and one is negative. Most hydrated salts are like that, not all. Then we have complex salts that are formed by mixing together two simple salts. Example, tetraamine copper. Okay, so you can already see ammonia is there and copper is there. Okay, and that can be prepared by mixing together copper tetraazote sulfate 6 solution and ammonium hydroxide solution. Those are the types of salt. What are the uses of salt? Number one, salts are used in the manufacture of agricultural and consumer substances like chlorine gas, fertilizers, and laxatives. Also, they are used as food preservatives. They're used as drying agents. They're used as antifreeze. And how can you prepare salts? One, by the action of dilute acid on a metal. So if you react a metal with a dilute acid, a salt is formed. Okay, like Zn plus 2HCl will form ZnCl2, zinc chloride, which is a salt, plus hydrogen gas. Number two, by neutralization of an alkali by an acid. Remember, that's neutralization reaction. An acid reacts with a base, salt and water is formed. So salt can be formed by that too. Also, by the action of a dilute acid on an insoluble base. Okay, then we have by the action of dilute acid on trioxocarbonates. 4. Those are the ways to prepare salts. Now, how can you recover soluble salts from solutions? We have different ways. Number 1, heating to dryness. So this method is only used when the soluble salts can withstand dry heating. So like most chlorides except zinc and iron 3 chlorides are recoverable from their solution using this method. Okay, so the salt solution is put in an evaporating dish and heated slowly to dryness to produce the salt in the solid crystalline form. And we also have crystallization method. This method is used when the salts can decompose or can be destroyed if you dry heat them. Okay, so trioxonitrates 5 and tetraoxosulfate 6 salts are usually recovered by crystallization method. How do you do that? The salt solution is first boiled, so that to reduce the amount of water. Then on cooling, crystals of the salt will begin to appear in the solution. Okay, sometimes just a speck of the salt is added to it to make it crystallize faster, or you just use a glass rod and scratch the bottom of the container in which the solution is in. How do we prepare insoluble salts? Very important. Number 1, double decomposition. So here 2 soluble compounds, one containing the metallic radical and the other containing the acidic radical of the required insoluble salt will be mixed together, like AgNO3 plus NaCl. Good. Will combine to form AgCl. Ag from AgNO3 and Cl from NaCl. And also NaNO3 will also be formed. 2 soluble ones. Okay, number 2, combination of constituent elements, just like you're cooking. Combine Fe with S to form FeS, iron sulfide. Alright, now hydrolysis of salts. Hydrolysis is a reaction of a salt with water to form a solution, which is either acidic or basic. Salts formed from strong acids and weak bases hydrolyze in water to form acidic solution, because there is the acid hydroxide, the hydrogen ions are more, so it's acidic solution. On the other hand, salts formed from weak acids and strong bases hydrolyze in water to form alkaline solutions. So we have to deal with water of crystallization. Now, when certain compounds are exposed to air, you see they will either lose their water of crystallization or they absorb moisture from their surroundings. Water of crystallization is the amount of water molecule that is present in any crystal. It's in the structure of the crystal. It cannot be visibly seen, but it's there, right? So some substances, when you expose them to the atmosphere or to the surrounding, they lose that water of crystallization. The first thing we're going to consider is efflorescence. Efflorescence is a phenomenon whereby crystalline salts lose part of their water of crystallization when exposed to the atmosphere. The opposite is deliquescence. Deliquescence is when the compound absorbs water from the atmosphere on exposure to the atmosphere. Now, like your salt in your house, carry it, keep it on a paper, keep it outside. Come back after a while. If you will see that salt is moist. If you shift it from where you kept it, you'll see traces of water on the paper, showing that it was absorbing water from the surrounding to itself. That shows you that salt is deliquescent. So deliquescence is another thing there. Then we have hygroscopy. A hygroscopic substance is that substance that will readily attract water from its environment, but will not dilute itself like a deliquescent substance would. It will just become sticky or moist. Okay, that's if it was solid, or if the hygroscopic substance was solid. It will not absorb moisture enough to turn into solutions. It will become sticky or moist. But if it was a liquid, that's like concentrated tetrahydrosulfate acid, it will absorb water enough to dilute itself up to about even 3 times its original volume. Okay, so hygroscopic substances are commonly used as drying agents. Okay, like quicklime, copper 2 oxide, and the rest. So most acids, bases, and salts are electrolytes. That means they can conduct electricity. But of course, since not all of them will dissociate their ions in water completely, then not all of them will have this same power, so to say, same effect as electrolytes. Alright? Generally, the conductivity of an acid or base depends on, number one, the amount of the ions present, and then if these ions are moving, their mobilities. Okay? A strong acid or a strong base will conduct electricity strongly because their number of ions are large. But a weak or acid or base will only conduct electricity weakly, as in very weak, because it contains a few ions. Alright, now we move to the next topic, carbon and its compounds. So carbon and its compound, we are slowly getting into hydrocarbons. Okay, carbon is a non-metal that we know it occurs naturally as diamond and graphite. Okay, carbon also occurs in an impure form like coal, and in the combined state as petroleum, wood, and natural gases. So other sources of carbon is mineral deposits like calcium trioxocarbonate 4, that's limestone, magnesium trioxocarbonate 4, that's edomite, and carbon 4 oxide, all those, that's in the air, has carbon also. So the chemistry of carbon compounds is known as organic chemistry. That's what we are going into now. Alright? Now let's look at allotropes of carbon. First of all, allotropy is the existence of 2 or more different forms of an element in the same physical state. So allotropes will be the different forms of the same element in the same physical state. Diamond and graphite are the 2 allotropes of crystalline carbon. So the others, like coal, that's the other allotropes, coal, coke, charcoal, lamblack, they are amorphous, they are not crystalline, they are not, they don't have a well-defined shape or size or structure. They are amorphous, they take the shape of whatever they enter into. Okay, now let's look at diamond. Diamond is the purest form of naturally occurring carbon. It's a colorless, lusterless solid which can be polished into precious stones. So it's not shiny when it's rough. So they used to call some talented people rough diamond. That means they're not been polished yet. It's when it's polished that it reflects light according to the angles created and becomes luminous, shiny or lustrous. Okay, so diamond crystal is octahedral. That's the shape of diamond structure. And we say it's crystalline structure. So because it has a well-defined shape and structure, so that well-defined structure or shape is octahedral. That means it has 8 sides. It is a giant molecule in which the carbon atoms are closely packed and held together by strong covalent bonds. Properties of diamonds. Diamond is the hardest known substance. So only diamond can cut a diamond. Diamond has a high melting point. Okay, it is very dense and resistant to high temperatures and chemical attack. It does not conduct electricity. Why? Because there are no free valence electrons in the diamond crystal, as all of them are used in bond formation. What do we use diamonds for? Diamonds are used industrially in drills. Because it's hard, then it can drill and penetrate into rocks. So drill bits are made from mostly diamond, so it's able to drill into rocks and pass through. Also for mining. Then it's also used as abrasives to sharpen very hard tools. There are very hard tools that can't easily sharpen, but since diamond is the hardest, it can sharpen those ones. It is used for cutting glass and metals. If you see people that do tiling, they have a particular device where they will just put the tile and roll the device on the line they want to cut, and it cuts. That's because that plays their role in the tip of it contains diamond, that can help cuts and other metals too, but diamond is mostly used. Then diamonds are also used as jewelries. The females should understand this better. Your necklace, your watch, your bracelets, and all that. Jewelries, some are made from diamonds. Or at least the diamond stone is the ring, head, and all that. Then we have the brother of diamond, graphite. Graphite occurs naturally as plumbago. It is formed by the action of volcanic heat on coal deposits. So graphite has an hexagonal structure. Okay, graphite is soft and will flake easily because of its layered crystalline structure. It has a high melting point, but it's less dense than diamond, so its melting point will not be as high as that of diamond because diamond is harder. Graphite conducts electricity. So unlike diamond, graphite conducts electricity. And this is an exam question also. I'll ask you, explain why graphite can conduct electricity, but diamond can't. You go ahead and say because diamond has no free valence electrons, no mobile electrons, because all those electrons are used in bond formation. But remember that graphite has a layered structure, which means it can allow one atom move over the other atom in layers. They are arranged in layers. So because of that, the electrons are free to move. They are mobile electrons, and that's why graphite can conduct electricity. What are the uses of graphite? Number one, graphite is an excellent dry lubricant. That's because it has a layered structure, of course. It allows one layer to slide over another easily. It is often used as electrodes in electroplating. When you do electrolysis, you understand that better. Then a mixture of graphite and clay is used as the lead in pencils. Okay, that's to tell you graphite is a constituent of lead in pencil. And then it is used as black pigment in paints. Okay, now all forms of carbon burn in excess oxygen to produce carbon dioxide only. That's why we are saying that all carbon atoms, when they burn in oxygen, will produce carbon dioxide as a product. Okay, now we said we have other allotropes, the amorphous ones, coal. Okay, coal, we have different types of coal. Brown coal, that is called lignite. Soft coal, which is called bituminous coal. Coal is used mainly as fuel to generate power for steam engines, factories, and electric plants. Okay, now when we heat coal in the absence of air, what that is called is destructive distillation of coal. And if we do that, that's if we destructively distill coal, we'll have four products. Number one, ammoniacal liquor, which is liquid. We have coke, we have coal gas, and we have coal tar. Okay, now remember, we also have charcoal as another amorphous allotrope. And charcoal, because it's important, I'm going to look at it, is made by heating wood, nutshells, bones, sugar, and even blood. So wood charcoal is the most common one, and is prepared by heating wood in a limited supply of air. And then let's go straight to why charcoal is important. Charcoal has a very porous structures. That means it has holes, tiny holes in them. And this hole allows small molecules of gases and colors to absorb, to adhere to its internal surfaces. And this is a good absorbent. Charcoal can be treated, to increase that adsorptive power. When you treat coal to increase its adsorptive power, then the product, the new coal, that's the charcoal that is then produced out of that treatment is called activated charcoal. So when charcoal is heated, the reaction opens up numerous more tiny pores on the charcoal, producing more surface area for adsorption. And I said that we call that activated charcoal. So you can, if you're asked to define activated charcoal is a charcoal that has been further treated to increase its adhering properties. Okay, uses of charcoal. Wood charcoal is used in gas mask. since it can absorb easily, then the poisonous gases won't pass through it without the poisonous molecules sticking to the walls of the charcoal. So I can wear it and enter into a poisonous place, and to be absorbing the poisonous gases, and only air will be coming to me. Okay, that's what is used for purification of noble gases and recovery of industrial solvents. Okay, wood charcoal is used as domestic fuels. Okay, then animal charcoal is used in removing the brown color from crude sugar. That's to say, charcoal can also be used in decolorizing petroleum jelly. And also, activated charcoal is used to remove coloring matter, okay, because of that adsorptive property. What are the oxides of carbon? That's when oxygen reacts with carbon. What does it form? You have carbon 2 oxide and carbon 4 oxide. We can also have hydrogen trioxocarbonates 4. Okay. Now, I'm going to state some uses of carbon 4 oxide. Okay. Most important that, okay, it's not the most important, but it's important to note that carbon 4 oxide is used in preserving drinks like Coke, Fanta, all that. So that's why when you open it, the gas that comes out, or when you drink it, you belch it out. Carbon 4 oxide. That's why it's called carbonated drinks. And the reason is to preserve it and also to give it that refreshing taste, that fizzy taste. When you drink Coke, you feel fizzy, you feel refreshed. If you open a bottle of Coke and pour it into a cup and keep it for 5 hours, the gases escape, and then you drink that, you see it's not refreshing anymore. Even if you make it cold again, it won't be refreshing anymore. So carbon 4 oxide was used to give that refreshing taste. Also, yeast and baking powder are used in baking to produce carbon 4 oxide, which causes the dough to rise. So he's saying that yeast or the baking powder is not what is making your dough rise. Yeast and the baking powder are agents to make carbon 4 oxide come into that dough. And when carbon 4 oxide comes into the dough rises. Okay, so gaseous carbon 4 oxide is used to prevent or to preserve fruit. All right. Solid carbon 4 oxide can be used as refrigerants, or maybe even gaseous carbon 4 oxide also. We also have carbon 2 oxide, which is produced by the incomplete combustion of carbon compounds, like in your exhaust pipes of car, motorcycle, generators. There's no enough oxygen to help achieve complete combustion. So it's going to be incomplete combustion, and the waste that is coming out in gaseous form is carbon monoxide, CO. Not enough oxygen to form CO2, so CO. Alright. Carbon monoxide occurs in traces as an impurity in the atmosphere. Okay, the percentage may be higher in areas where the gas is released in the exhaust fumes of motor cars. That's to say that in cities, the amount of carbon monoxide impurity in the environment is more than that in the village. In the villages, you have bicycle, you hardly have motorcycle, but you don't have cars as much as you have in cities. So the environment in that village is safer because carbon monoxide is not released into that air in a large quantity. But in cities, it's more. You see a lot of cars, you see generators and all that. Okay? Then carbon 2 oxide is a poisonous gas. That's why we're discussing that. As little as 0.5% of it in the air may cause a person to die. Okay, that's why it's not good to put on gen and stay in the same house. Put on gen is inside the house. By the time the carbon monoxide comes into the house, you breathe it in, cuts out the hydrogen supply in your system or in your blood, and cuts out the oxygen supply in your blood, and then no oxygen again for you to breathe, and you suffocate, right? And die, not you. Okay, so uses of carbon monoxide then. The reason why this carbon monoxide is even more dangerous is that it doesn't have a color. So you buy a new generator and put it on, and say, okay, there is no smoke because you're not seeing color. No, carbon monoxide has no color. And whether your generator is new or your car is new or old, carbon monoxide will be coming out because the engine didn't have enough oxygen to achieve complete combustion. So it's always going to be incomplete combustion, which is always going to yield carbon monoxide, CO. How do you test to distinguish between carbon dioxide and carbon monoxide? Carbon dioxide will turn lime water from its color, which is colorless, to milky color. That's how to know that substance is carbon 4 oxide. And also, if that substance is not warm, because carbon monoxide can do that if that solution is warmed. But on normal room temperature, if it's carbon monoxide, CO, you put it into lime water, it will not turn milky. It will remain that way, except you carry that solution and warm it, supply heat. Okay. Then we have trioxocarbonates. Okay, trioxocarbonates. 4 acid is very important. It's a basic acid, a diabasic acid. It forms 2 salts. In normal trioxocarbonate 4 salts, and the acidic hydrogen trioxocarbonate 4. Okay, trioxocarbonates 4 are formed naturally when trioxocarbonate 4 acid, which is formed when carbon 4 oxide dissolves in water, reacts with free metals, react with metallic oxides or other dissolved salts. So metallic trioxocarbonates 4 are usually found in natural ores and deposits. Okay, that is carbon and its compounds, and we enter into the last topic to conclude SS1 revision: hydrocarbons, organic chemistry. Now, hydrocarbons are compounds that are composed only of 2 elements, carbon and hydrogen. That's why it's called hydrocarbon, only hydrogen and carbon. So if there is a compound that contains only hydrogen and carbon, then that's a hydrocarbon. Okay? Alright, so it is classified into 2 main classes. We have the aliphatic hydrocarbon and we have the aromatic hydrocarbon. Aliphatic hydrocarbons are compounds of carbon chain. Okay, they are like chains, 2 ends open, carbon linked to another carbon, but the end carbon, the 2 ends are open, not joined together. That's how aliphatic compounds are. Now, these aliphatic compounds can be acyclic or cyclic. When they are acyclic, the carbon chains are straight, just like I just explained, but we can join the 2 ends for it to become a cyclic aliphatic hydrocarbon. Alright? Then we have aromatic hydrocarbons. As the name implies, aromatic is derived from the fact that many of these compounds in the early days of discovery, they were oils with fragrant odors. So aromatic compounds are cyclic compounds. They contain benzene ring as a basic unit. So how do you know if it's an aromatic compound? It must contain the benzene ring. Okay, so we'll say aromatic compounds are benzene and benzene-like compounds. That's benzene itself is aromatic, and other compounds that have benzene repeating units, or at least 1 benzene unit in them. Now, just like we have parents, we have generation, we have forefathers. So our names carry our generation and we are able to represent. Hydrocarbons are like that too. Can group them into families, but we don't call them families. We call that homologous series. So a homologous series is a family of organic compounds which follows a regular structural pattern. Just like in a family, you look like your father or your mother. You can have the characteristics, you can have the complexion, you can talk like them, depending. Homologous series, they have a regular structural pattern. That's how you would know that this compound belongs to this particular homologous series, and that's what I'm saying. And each successive member will differ in its molecule by a CH2 group. That means CH2 will keep adding to the next members to form their structures. Okay, so we have the different homologous series, but we're going to discuss for now alkane, alkene, and alkyne. Okay, so alkanes have the general formula CnH2n plus 2, and the simplest member is CH4 methane. Alkene has a general formula CnH2n, no plus 2 this time. And the simplest formula is CH2CH2, that's C2H4. And alkyne has the general formula CnH2n minus 2. Okay, so alkane CnH2n plus 2, alkene CnH2n nothing, alkyne CnH2n minus 2. All right, we have others, but that's what we're going to concentrate on. What are the characteristics of homologous series? Number 1, homologous series have the following common characteristics. All members share a general molecular formula. Number 2, each successive member in a series differ in its molecular formula by the addition of a CH2 group, I've already said that, and in its relative molecular mass by an increase of 14. The physical properties, number 3, example boiling point and melting point, of the members in any homologous series will change gradually as the number of carbon atoms per molecule increases. That's as you're increasing the number of carbon atoms, the melting point will increase, the boiling point will increase. Then the physical properties, okay, the members show similar chemical properties, and all members can be prepared by using the same general method. Okay, that's the characteristics of a homologous series. Then we have what is called alkyl groups. So alkyl groups include all groups that are derived from the alkanes by the loss of a hydrogen atom. So let's say we have an alkane member, but if it loses one hydrogen atom, then it becomes an alkyl group member. Okay, we're going to discuss alkanes, alkenes, and alkynes. Let me just finish all these preambles. So alkyl groups have a general formula CnH2n plus 1. And you have example methyl, ethyl, propyl, butyl, pentyl. You understand that soon. Then we have functional groups. Now the alkyl group of a compound is not reactive like that chemically, because they have stability of the carbon and hydrogen bonds. Now the chemical reactivity of an alkyl group is determined mainly by this substituent group. That's what we call functional group. So a functional group is an atom or a radical, that's a group of atoms, or a bond, can be double bond, can be triple bond, that is common to a homologous series and which determines the main chemical properties of the homologous series. So functional group is the most important to tell you the properties, the characteristics of that family. Okay, now each functional group has its own characteristic properties, and these properties are transferred to the alkyl group which it is attached to. Okay, so there are different functional groups. Alkanols have the functional group hydroxy. The symbol is OL. There is also fluoro, bromo, iodo, Cl, Br, I. Okay. Alkanon is a functional group. Then alkanal also, alkanoic acid, COOH, is a functional group, and all that. Take note that the functional group determines the basic chemistry of a compound, while the alkyl group affects the physical properties of that compound. So if the chemical properties does not change, then it's still going to have the same chemistry, boiling points, same properties that before. Now we get to saturated and unsaturated compounds. Okay, if an organic compound contains atoms joined only by single covalent bonds, the compound is said to be saturated, like alkanes are saturated. But if an organic compound contains carbon atoms joined by double or triple bonds, in other words, you want to see multiple bonds, then that's an unsaturated hydrocarbon or compound. Okay, so the alkenes and the alkynes are all unsaturated hydrocarbons. Okay, so now let's look at the aliphatic compounds before we go to aromatic. I'll finish the preambles now. We said that compounds whose molecules are composed of chains of carbons atoms are known as aliphatic compounds. Now, the ability of hydrocarbons to bond to themselves, like carbon linked with another carbon to form chains, is called catenation. Okay, so this catenation allows hydrocarbons to form more complex molecules because there is no limit to the number of carbon atoms in a given chain. Okay, so aliphatic compounds can be cyclic or acyclic. Cyclic means the two ends are joined, but acyclic means they are in chains, like open ends, like I said. So the first homologous series under aliphatic compound is alkane, and the alkanes are aliphatic hydrocarbons which form a homologous series of saturated hydrocarbons. They have the general formula CnH2n plus 2, and in each alkane member, all the carbon atoms are tetrahedrally bonded. That means the carbon atoms bond on the four sides, up, right, left, and down. Tetrahedral, tetra 4. Okay, bonded to the hydrogen. So the members of the alkane family in hydrocarbons, in organic chemistry, one carbon atom is called meth, meth. So because alkane has only one carbon atom, it's called because the first member of the alkanes, methane, has one carbon atom. That's why you have the name methane. So 2 carbon atoms means eth. So that's why C2H6 is ethane. 3 carbon atoms means prop, P-R-O-P. That's why C3H8 is called propane. 4 carbon atoms in chemistry is called butes. That's why C4H10 is butane. 5 carbon atoms in organic chemistry is called pent. That's why C5H12 is called pentane. And that's why C6H14 is called hexane. That's why C7H16 is called heptane. C8H18 is called octane. And C9H20 is called nonane. And then C10H22 is called decane. DECANE. Okay, all those you can simply draw your structures. This is a revision. There are resources on the lecture playlist where you can see full lecture on them. This is just a revision, so you can go there and see how to draw the structures of all these, watch them and share them. Okay, you will also see there the rules for naming hydrocarbons, but know that I've already told you that 1 carbon atom means meth. So you already know that compound, if it has only 1 carbon atom, is already methane. If it's now an alkane homologous series. So meth coming from the number of carbon atoms, then the ane ending, the ane coming from the alkane family. Just like, let's say my name is SCITH and my family name is Lab, L-A-B. So I'll be called SCITH Lab. Okay, the meth or the eth or the prop or the butes and so on is the number of carbon atoms that compound has, and the ane if it's an alkane, or the ene if it's an alkene, or the yne if it's an alkyne, comes from the family name. You see more of this in the videos. Let's go to organic chemistry. There are 3 videos there: organic chemistry 1, organic chemistry 2, and organic chemistry 3. 3 of them will give you full and complete O-level knowledge on organic chemistry. You see all the rules for naming hydrocarbons there, naming alkanes, alkenes, and alkynes, the structures, and all that. Okay, how do we prepare alkanes from unsaturated hydrocarbons? You can also prepare from alkyl halides. Halides are halogens, and also from carboxylic acids. Okay, remember that all carbon atoms, when they burn in air, will produce carbon dioxide and water. So carbon dioxide must be produced. So that means all hydrocarbons, when burned, will produce carbon dioxide because hydrocarbons contain carbon atoms. And then we have the different types of reactions. We have addition reaction, we have substitution reaction, and then alkanes undergo substitution reaction. This is why, the bonds, alkanes have tetrahedral bonding, so the carbon atoms are bonded on the 4 sides and complete enough hydrogen to bond it. So for you to bring in something else into an alkane member, you must remove one thing, and that's what substitution is about, right? You remove one thing and then bring another thing in. That's the only reaction that goes well with alkanes. A substitution reaction involves a direct displacement or replacement of an atom or group by another atom or group. Okay, so alkanes are very inert and do not undergo any reactions other than combustion, burning, and substitution reactions. What are we using alkanes for? Natural gas, your methane gas, your cooking gases, butane, those are alkanes. Then methane is used for making hydrogen, carbon black, carbon 4 sulfide, alkynes, trichloromethane. And trichloromethane is an antiseptic which is used in surgical operations. Okay, they're also called chloroform. Then tetrachloromethane is an organic solvent which is known as carbon tetrachloride. Alright, so butane is used in cigarette lighters. Butane. Then octane is used as fuel in internal combustion engines. Alkanes from nonane to hexadecane are used as diesel and kerosene. Alkanes with 17 to 35 carbon atoms form the major components of lubricating oils. They also act as anti-corrosive agents, of course. And then solid alkanes are made as paraffin wax in candles. And alkanes with chain length above 35 carbon atoms are used in road surfacing, bitumen. Okay, so I've also talked about alkenes, but I'll summarize it. Alkenes are homologous. It's a homologous series of hydrocarbons with a general formula CnH2n, and the n must be a positive whole number which is equal to or greater than 2. CH2 does not exist. So we said the simplest member of alkane is methane. The simplest member of alkene is not methane because one carbon atom does not exist in alkenes. So it's ethene that is the simplest member then. So ethene is the first member of the alkene series. Propene, but 1 in and but 2 in are colorless gases at ordinary temperatures and pressures. The next 13 members, that's C5H10 to C17H34, are liquids, okay, while the higher members are solids. Alkenes burn with a more luminous and smoky flame. I said the more the carbon atom, the more the boiling points, melting points. Same way, if you have more firewood in the fire, you have more fire, you have more smoke. So the more the carbon atoms, the more flame it can bring the more smoke it can bring when burning. Alright? And then we have the members of the alkene series: ethene, propene, butene, pentene, hexene, heptene, octene, nonene, decene, and dodecene. Remember to check that video and understand all this completely. There are rules for naming alkenes and alkynes there, but they're almost like the same. But the rules are rules. You must follow them to be able to name them. Please make sure if you want to pass hydrocarbons, you go to those videos and watch the 3 of them completely. They are long, but they are long because they are very necessary. It was important for me to highlight every single detail and not leave out anything. Okay, so go there and you understand those areas more. Now, alkenes can undergo both substitution reaction and addition reactions. So addition reactions, that's because alkenes and alkynes, they have double bond, and you have a double bond or any multiple bond because there are not enough hydrogen to bond with those ones, so they just bond with itself and give a double bond or triple bond. So that's to say, if there were enough hydrogen atoms, there wouldn't be double bonds. That means hydrogen atom can be added to those bonds. So it's addition, that's addition reaction for alkenes and alkynes. So you can also take away one constituent that was already there and put another one. That's why it can still undergo substitution reaction, but will undergo addition reactions also. So in an addition reaction involves the direct addition of an attacking reagent across the double or triple bond of an unsaturated compound to yield a saturated product, and at least a product in which the degree of saturation is increased. Now, alkenes, what are we using them for? Ethene is used in making plastics and synthetic rubber. And that's what you call polymerization. And low concentration of ethene are used to haste or to fasten the ripening of fruits. As artificial ripening of fruits, you can use low concentration of ethene to do that. Ethene is the main source of many organic compounds like ethane, ethanol, etc. So in that sense, we've also done alkynes, but generally alkynes are homologous series that have the general formula CnH2n minus 2. Alkanes have single bonds. Alkenes have double bonds. Alkynes have triple bonds. At least one triple bond in the chain, in the compound. And so you can easily say one bond is called N, double bond is called IN, and triple bond is called IN. Alright? I'm not saying all the carbon will be having double bonds or triple bonds. At least one of it will have a triple bond if it's an alkyne, and will have a double bond if it's an alkene. Okay, so the members of alkynes is ethyne, propyne. See the eth from the C2, 2 carbon atoms, and the ine from the family name alkyne. Okay, so ethyne, propyne, butane, pentyne, hexyne, heptyne, octyne, nonine, and decyne. Those are the members. There are more, but just want to mention that. And you prepare alkynes from the dehydrohalogenation of alkyl halides or dihalides, and also from vicinal dihalides and from calcium carbide. Okay, but in the laboratory, alkynes are prepared by the action of cold water on calcium carbide. All right, in large-scale production of alkyne, calcium carbide, that's CaC2, is made to react with water. It is prepared by heating quicklime in the presence of coke, and quicklime is obtained by introducing limestone to heat. The reactions for the preparation of ethine is CaCO3 limestone yields CaO plus CO2, and then the CaO is combined with carbon atoms to yield CaC2 plus CO, and then the CaC2 is combined with water to yield calcium hydroxide plus ethine, C2H2. Alright, so ethine is still an hydrocarbon, so when it bonds it will form, it will produce carbon 4 oxide and water, but carbon 4 oxide must come out. So I've said already that addition and substitution reactions can also be undergone by ethynes, but ethynes then adds polymerization reaction. So ethine can undergo addition reaction, substitution reaction, polymerization reaction, because ethine polymerizes to form aromatic hydrocarbons like benzene. Okay, now it's important to take note of the test for unsaturation. Unsaturated compounds are best recognized by their addition reactions, but the most convenient test is the reaction with bromine water or acidified potassium. So when you bring an unsaturated compound and you add them to bromine water, the bromine water will change color from the reddish brown color of bromine water to a colorless liquid. That's unsaturated compounds decolorizes bromine water. Alright? And what do we use alkynes for? Ethine is mixed with oxygen to produce a very hot and easily controllable flame. That's oxyethylene flame, which is used by welders to cut metals. Then ethine is used in drying or dry cleaning as an absorbent to dissolve grease. Okay. Now we've done aliphatic compounds. Now aromatic compounds are benzene and compounds that resemble benzene in chemical behavior. and the structure of benzene is benzene has C6H6, and then other compounds that resemble benzene, the aromatic compounds, are phenol, toluene, xylene, pyrrole, furan, thiophene, and all that. Okay, you'll be given the structures in your exams and you ask what is that, and you identify. So no, phenol has hydroxy group, alcohol group, functional group present in it. Toluene has methyl group, CH3 present. Xylene has 2 CH3 atoms or 2 CH3 present in them. Pyrrole has nitrogen, furan has oxygen, thiophene has sulfur. Take note. But the physical properties of benzene is that, number one, benzene is a colorless liquid with a sweet smell, aromatic compound, and it is insoluble in water as benzene. It has a boiling point of 80 degrees Celsius. The chemical properties of benzene is that benzene undergoes substitution reaction and addition reactions. Okay, of course, so benzene can also be looking at alkene, benzene, right? The uses of benzene. Benzene can be converted to styrene, and this styrene is used in the manufacture of synthetic fibers like nylon. Okay, you remember alkenes can be polymerized to plastics, nylon. Benzene is an important source of chemicals which are used in pesticides and detergents. Then toluene, which is also an aromatic compound, is a benzene derivative, is used in making explosives. Phenol is used as a disinfectant and a raw material for making plastics. And aniline type compounds are used for making dyes and drugs. Alright, now let's also revise alkanols. Alkanols are compounds in which hydroxy group, the OH group, are linked to alkyl groups. We can use R to represent alkyl groups. And we say alkyl groups are formed when an alkane member loses one hydrogen atom. So they are derived from their corresponding alkanes by replacing the hydrogen atoms with hydroxyl groups. So the hydroxyl group is the functional group of the alkanols and is responsible for their characteristic chemical properties. So most alkanols contain only one hydroxyl group in their molecule, and these are referred to as monohydric alkanols because they have only one hydroxyl group, monohydric. And the monohydric alkanols form a homologous series with the general formula CnH2n plus 1 OH plus 1 then OH. CnH is 2n plus 1 then OH. And since the group is the CnH2n plus 1 is an alkyl group, we can say R because R can represent alkyl group, then OH. So we can say ROH is the formula for alkanols, monohydric alkanols. So the name of each homologue is derived by dropping the N ending. It was alkane, so we remove the E of alkane and now put OL. So it becomes, if it was methane, remove the E and it becomes methanol. That's how alkanols is formed from alkane members. So if it was ethane, what's the alcohol name now? Ethanol, propanol, butanol. That is how they are named. So the simplest member of the alkanol series is methanol, as CH3OH. And sometimes it's called wood spirit because it was produced by the destructive distillation of wood in the early days. Take note that methanol is poisonous and can cause blindness if consumed. Ethanol, C2H5OH, is the second member of the alkanol series, but is the most important member of that series. It's an essential ingredient in alcoholic drinks. Ethanol is what makes you high. Ethanol is what's in your alcoholic drink, not methanol. So ethanol can simply be called alcohol in some cases. So generally, hydrocarbons are not soluble in water, but alkanols are soluble in water. And why? It's an exam question. Because the hydroxy groups in the molecules of alkanols can form hydrogen bonds with water molecules. Okay, so solubility of the alkanols decreases as the number of carbon increases. So the alkanols can become less soluble than it was if the carbon atoms have increased. So methanol is more soluble than ethanol, because the carbon atom in ethanol is 2 more than methanol. Methanol is just 1. So decanol, if possible, that has 10 carbon atoms, will not be as soluble as ethanol, and so on. Okay, now the types of alkanols, there are 3 types of alkanols. We have the primary alkanol, the secondary alkanol, and the tertiary alkanol. A primary alkanol has only one alkyl group attached to the carbon atom that carries the hydroxyl group. A secondary alkanol has 2 alkyl groups attached to the hydroxyl group. Okay, attached to the carbon atom that carries the hydroxyl group. You can see it on your screen. And then tertiary alkanols will have 3 hydroxyl groups attached to the carbon atom that is carrying the OH, the alcohol, the hydroxyl. It has 3 alkyl groups attached to the carbon atom that is carrying the hydroxyl groups. Those are the primary, secondary, and tertiary alkanols. Okay, so the last thing is isomerism. Now, isomerism is the existence of 2 or more compounds with the same molecular formula but different molecular structures. Isomerism is also long. For you to understand, it has to be the full video. It's in that organic chemistry questions. I think that's organic chemistry 3, because that's the last part. So you can go straight to organic chemistry 3 and watch isomerism completely. Okay, now, so I said isomerism is a compound has the same formula, but you can arrange them in different structural forms. Then those different structural forms of that compound with the same formula are isomers. Okay, so isomers can be split into 2 broad groups. We have structural isomers, and then we have stereoisomers. Structural isomers examples can be chain isomers, where you change you form chains. Okay, then position isomers, you can change the positions of the functional group in the chain and form new isomers. And then we have functional isomers, same thing. And then for stereoisomerism, we have geometric isomers, which is where we have the cis and trans isomerism. And then we have optical isomerism, which we have enantiomers, optical isomers. Alright, so you go to organic chemistry 3, just go through the playlist in this channel. Go to playlist, open lecture playlist. When you open, go down, you will see those were the first set of topics I taught. So you will see organic chemistry 1, organic chemistry 2, organic chemistry 3, as well as other topics in chemistry. Go through them and you will understand organic chemistry completely. Since it's a revision, this is the end of SS1 chemistry. The next revision that will be coming up will be for SS2 and then later SS3. So with these 3 set of videos which are meant for SS1 revision, after reading, or you can just keep it, play it with you and play it and by your side, and you'll be remembering the topics, and then listen, share it to your friends that are writing exams so they can pass as well. Do well to subscribe to this channel. We bring you what will help you most in your endeavors as an academic personnel, as a student. You want to succeed, you want to pass with flying colors. We do our best to teach in the best possible way for you to understand. We bring them down to the lowest term for you to understand. We'll also be having videos of practicals. We'll have specimen analysis to prepare you for WIAC exam and practical exams, biology, agric, physics, chemistry. We'll also have revisions for other subjects. We'll also do NECO, we'll do JAM, we'll do other exams, GC also. So do well to listen attentively to all these contents and you will pass your exams well. Thank you. God bless you.